incentives of games in large-scale computers.
Thank you, and thank you very much for the invitation. I do realize some of you have seen that talk before. I'm looking at you. If you want to have a nice walk with the weather, feel free. And anybody else, I apologize for giving that same talk here before. So I'm going to talk about incentives and games in large-scale mobility. And the first thing I'd like to do in this, assuming the slides are going to show, is to talk about a general framework for traffic operations that is, I think, an underlying frame for what we're doing here. And then it will bring me into inference and games. So I always like to start this talk with this picture I stole from Richard Murray's controls book at Caltech, which is what every undergrad learning control probably sees first, and which is a very good frame of many systems that we're trying to control. And then trying to use that frame to walk through the modeling and control of the transportation systems we do, try to explain in each of the blocks what almost half a century of contributions have led to and where that brings us today. So starting with the systems dynamics, there is literally almost half century of modeling of these kinds of phenomena that have manifested itself by, we just did a quick inventory. There's 900 articles in the last 3 decades or 4 decades on PD models just for freeways, and the numbers for articles is even larger. So there's a vast amount of models to rely on. What's interesting is when you look at the sensing infrastructure for sensing these systems, we've been for many, many decades in a situation where only a very tiny proportion of the network is actually instrumented, mostly because deploying things like loop detectors of camera is costly, and it's nearly impossible to cover all of the network, leaving the transportation network as a very ill-measured and sparsely measured system. And if you think about the control infrastructure, it's not much better in that, think about controlling traffic at the scale of a corridor or a scale of a city. Obviously, you have traffic lights in the city streets. You have maybe some more advanced ways to manage lane-by-lane traffic in intelligent corridors. You have metering lights, and that's pretty much all there is. And so if you take a place like the I-210 corridor, we're currently operating in California, just to manage the mobility of hundreds of thousands of people who go through this corridor every day in both directions. The total number of assets is 450, which is extremely tiny. And you can imagine that it's pretty insufficient to manage mobility efficiently. And that's a reality of most of the traffic planners and traffic operations engineers in the US and in many places in the world. Now, when it comes to building a controller, there's 2 key ingredients which have radically changed over the last decade and will continue to change over the next decade, mostly due to the explosion of the cell phone industry, and that have led to interesting situations that are currently making the system pretty unstable. So first, thinking about estimation, the process of estimation of traffic is the process of understanding the current state of the system, given the sparse measurements one has, which in traffic engineering is often represented in the form of a time-space diagram, which you can view it as a picture which over time depicts the level of congestion along the freeway for the stretch of road you're interested in. And so that's called nowcast. And then in terms of demand forecast, there's little data available, or at least until a few years ago. But what you're looking at here is essentially a prediction of what the amount of people that will come into your network. So something like a curve that shows you the morning peak and then the evening peak. And that's mostly based on our historical data or data collected at the few places where you can measure this. This usually is fed to some form of optimization. So traffic engineers trying to make traffic flow better, which you could graphically encode this as trying to make everything green flow. Reality is obviously very different. And that is usually fed to a human because in almost no places in the world will the infrastructure at this point be operated automatically. So at the end of the day, there's a bunch of recommendations made to people in the traffic command centers, and they use these recommendations to operate the system. And this is 2 snapshots of the D7 headquarters in Los Angeles and the LA Metro headquarters, also in Los Angeles, which are the 2 organizations in charge of the LA traffic. And the system that they're running is a system we're currently building for them, and that will be launched fully in 2019. So one thing which is interesting here is that in general, I mean, for people thinking about optimization, you think about a feasible set, and the real question is what you can do with a system. And so when it comes to the world of operations, one of the important things is that you don't have an infinite feasible set, and that there's very few things that the different jurisdictions in charge of the space and the infrastructure will let you do. And so typically, the way things are done in practice is whoever is in charge of that jurisdiction writes down a concept of operations, which you can view as the feasible set of playbooks that are admissible by the practitioners in charge of that ecosystem. And so essentially, it's a long document, which in the case of the I210 our team wrote, which presents all the possible things that the different cities in charge of that corridor will accept. Such as, for example, if there is a major accident with a truck going over the rail line, using an on-ramp to make traffic exit the freeway, which is not a typical mode of operations, I guess, of a freeway. And so I think what's interesting historically is that the way these systems have been run over the, I would say, last half century is with very little data. And I think what the last decade has brought is a lot of available information, which initially has been used really well, and which, with the emergence of routing apps as a predominant tool for motorists to guide themselves through the network, is being very radically disrupted. So starting with demand and forecast, which is essentially what you would want to operate your network, the major disruption we're seeing happening now is the fact that cell phone companies, for example, like AT&T, nowadays have up to 40% of the population in some states, for example, in California. And what that means is that because they have access to all these cell tower records, they can know the approximate location of 40% of the population in real time within 400 meters or half a mile, which is roughly the accuracy that you can get from triangulation or trilateration. And what's really interesting about this is that even though that data is not publicly available and that there's some proper institutional interfaces that are needed to use that data, such as Sidewalk Labs and others, what it's currently doing is it's enabling the MPOs and the public organizations that are in charge of modeling that demand to completely change the accuracy at which they're operating. Because you can write simple problems such as OD, origin destination inference, in the form of convex programs, which are fairly simple. They have gigantic null spaces, but they're fairly simple, and they encode the potential routing of the different agents in the network. And essentially, that provides a sense of what the demand on the network is. So let me show you what the data looks like to give you a sense. So this is what you see in blue is a bunch of trajectories of a few vehicles collected from AT&T CDR records. And then one of them in particular is outlined here. That's an example of a vehicle traveling through LA. You can see the location is pretty inaccurate because at some point he's talking to a cell tower that is off the freeway. But the point is, if you're doing demand estimation, that's good enough, because what you care about is you care about aggregate demand from some geographies to some other geographies, and that is data that is well suited for this. This is another example of a FedEx truck that is doing a lot of pickups and deliveries. That's someone commuting to work, stopping in the middle, and so on and so forth. And what's very interesting about this is that until recently, the only way for public agencies to access that type of demand was to essentially use census data. So actually, we're talking a lot about the census these days in the news, as many of whom have heard, and the problems associated with it. And so typically, the way you would get access to demand information is by knocking on people's doors and asking them where they work, where they live, when they commute, and so on and so forth. And that entire way, and for example, the SCAG model in California, in LA, has been built on that kind of data. And with these new types of inference problems you can solve, there is really the hope that one can really bypass and leapfrog the state of the art using census data. And to give you a sense of what the type of things that can be done is that obviously these are problems which are very ill-posed because their null spaces are fairly large. But if you do plot the type of parameters that you would want to see in doing this inference, then you can show that accuracies can be pretty good. So for example, when you go to a given location and you query your phone, it usually gives you 1, 2, 3, 4 routes maybe. So if you limit the number of potential routes that people could use from one location to another to 3, well, then the accuracy you might get, depending on the grid and the granularity of the spatial data you get, might not be that good. But if you actually increase this number of routes, so allow for more options, then you can get to really good accuracies with, sorry, the pointer's dead here, with a tessellation of the space that is pretty relevant for what you have in LA, which is roughly shown here by 1,000 towers per location we're looking at. And so the high-level point I'm trying to make here is that that's very important.
Relative to what is the error measure?
So here, the run we're doing is to assess the accuracy is we use synthetic data to assess the accuracy, because otherwise we don't have a travel model, and feed it into the model. And then obviously we see similar convergence plans with the real data, but the real data we can't assess because we don't have ground truth. So, so that's for demand and state forecast. For state estimation, over the last decade, we've seen a lot of disruption of what's happened in the field just because of the emergence of GPS data. And so going back to that state space diagram I'm showing here, typically in order to have a good sense of what traffic look like, what you would want is you would want to have a colored space time diagram like this, in which for each time and each location, the color indicates the level of the speed. So just assuming, for the sake of the explanation, that initially you have no data, if you were able to measure data along loop detectors at fixed location, what that means is that for all these black lines here, you would be able to measure the number of cars going through the given point. It's a flow. And if the sensor fails, then you don't have data. It's also, except maybe in places like LA, usually you can initialize a model at midnight by assuming that the level of vehicle on the freeway is pretty small. And the revolution which has happened with the emergence of the cell phone is that using the terminology of environmental sciences, you can actually do Lagrangian sampling, which is if you can track a vehicle through its GPS location, you can essentially measure the speed of the vehicle along the freeway, from which you can infer a few things. Not flow, but you can infer other parameters of the models. And if you cannot track the vehicle, but just identify it at specific locations, like with fast track, or if you have super low frequency GPS, then what you know is that the value that this car is the same as this car. And so part of the contributions that we made over the last decade in this field is essentially coming up with a lot of inverse modeling algorithms that enable the reconstruction of this surface. And it turns out that we know since 1968 that the surface, so if you view this as a 3D plot, is the solution to a Hamilton-Jacobi equation. It's something that was discovered by an engineer called Carl Moskowitz at Caltrans. It's kind of visionary at the time. This is why the variable in the Hamilton-Jacobi is named M in honor of Moskowitz. And so essentially what you're saying by this is that the underlying dynamics of that system in that diagram I showed before is this Hamilton-Jacobi equation. And so doing inference here is essentially saying that you're sampling that function at a given location. If you're using loop detector data, that you can initialize the value of the function if you have an assumption of what traffic is like at midnight when the freeway is nearly empty, and that looking at the models, that function is constant along a trajectory, assuming that you can ignore people passing each other, which again is an assumption that sometimes is valid, sometimes isn't, but then provides you an isoline of the function, and if not, at least the fact that this car being the same as that car says that the function is the same. And so a lot of the work that we've been doing in this field over the last 10 years is essentially coming up with inverse modeling algorithms that can provide estimates of the value function of that Hamilton-Jacobi equation, which we all know is nasty because first it only has a weak solution, and even that weak solution is not well behaved. It's depending on the framework you use, it can be as bad as lower semi-continuous, which is not even continuous function. But the beauty of the framework is that one of the things we're able to show is that if you assume that all the data you're dealing with is piecewise affine, which is for practical purposes very good because you just make the discretization small enough, then you can show the existence and uniqueness of solution to the problem. You can even compute the solution explicitly, and you can formulate the problem of inverse modeling as convex programs, which was a big contribution when we found this out, and that was based on the first book we published 6 or 7 years ago, and we're now writing the second part with all the different other problems we could solve with it, in particular controls problems. So to give you a sense of what these methods look like, in specific cases, we were able to collect super high frequency data. This is an example of 3-second sample GPS data collected for 2% of the population. So it's like low density, but very high resolution. And 2%, I mean, just that's only a few of us in this room carrying a phone. That would be enough. What I'm going to show is that if you apply these methods on an even more degraded subset, like this one, you can essentially reconstruct with these convex programs the actual value of the function quite accurately. And so for this one, we had a lot of ground truth data also collected from video data, and therefore we're able to show that these methods perform really well. So the interesting part is that if you look at the historical evolution of the penetration of smartphone in the population, these problems were really interesting to solve when only a few percent of the population were carrying them. Nowadays, major access providers have up to 100% coverage because between, for example, if you're Google, between people carrying an iPhone and running Google apps and people having an Android, essentially they can access to nearly the entire population's data. So in a sense, the inference problem is maybe not so relevant anymore. But what's interesting with it is that from that resulted a situation in which now traffic information has become ubiquitous, and that first trend started essentially in 2008 when these very first phones were emerging, and nowadays everybody has this type of information for free on their phone all the time. And so the question I'd like to address next is what can be done with this information? So let me fast forward a little bit and show you just an example of what that data looks like. This is an example of 500 vehicles sampled every 30 seconds in San Francisco. And what you can see is that if you let that data play, this was from the very first system we built in this field. If you let that data play after a while, you'll see you can trace the entire map. And just to give you a sense of the scales, the last time I saw numbers of Lyft and Uber drivers registered for San Francisco, the number of vehicles I saw was 40,000, I believe. So you can imagine the scales at which that data exists today. And so the next question I'd like to tackle is, all these problems of inference essentially have been fairly well studied. I think it's a fairly mature field in which we've been very active for the last 10 years. And now the question is, what can be done with that data, and is that necessarily good? And that brings into the other topic of the talk, which is games and routing. So think about the process of how anybody who is using a router, whether it's Google, whether it's Waze, whether it's Uber or Lyft's internal routers, whether it's INRIX, whatever you're using, essentially you're pinching an origin, a destination, and usually it gives you 3 routes, which are the 3 top routes. And in general, the way it selects them is that it'll give you a preferential route, and it'll give you 2 routes for which the travel time is not too different. And so what that does to the dynamics of the system is that it essentially adds a feedback loop into the plant. Because models for this have been known for a while. Routing patterns of people have been known for a while and have not evolved fast historically until that information became available. But if now you have hourly by hour or even minute by minute information, that will drastically affect the speed at which you're making decisions. And obviously, the main problem with that is that the control infrastructure is not able to adapt to this because this is moving much faster. And this might seem a bit of an academic problem just presented like this, but it's something which is very real. And I just would like to show you a few news items over the last 18 months that we collected to give you a sense of the scale of the problems this is actually creating. And so the beginning of the story is the statements made by elected officials with some companies stating that, if you give everybody free information, which is allegedly optimal for them, you're improving society. And I can see a lot of people doing game theory already laughing. That means you probably understand what's coming next. What's coming next is that people start to realize the inconvenient externalities, if you will, of this type of information on the specific traffic patterns in their neighborhood, which, by the way, might not be bad if you look at global optimum outcome of the process, but certainly not good locally. And if, by the way, you have seen a lot more traffic in your neighborhood, you're not alone, as you can tell from all these headlines, which I'm going to keep flashing through. Getting to an interesting point here is that at some point, people started to get really fed up of this, which led to interesting outcomes, such as trying to resist. So first, it was kind of funny. About 18 months ago, you started seeing people in the news waving, signs saying, "Shame on you for going through my neighborhood." Okay, that's a bit anecdotal until people started to get more organized and posting fake detour signs to confuse people, paying senior citizens to carry phones, running the app along the street, hoping to spoof the learning algorithm that computes travel time. So that's an interesting and creative way of doing this. In fact, there are manuals on how to spoof apps. You can find them on the web. And then the resistance gets even more organized. This is an example in Fremont in which a city starts to, on purpose, changing the cycle times of their traffic lights to prevent people from leaving the freeway. So that creates a huge backlog on the freeway so that people don't come into their neighborhoods. So that's now interesting because this is, in a sense, steering the system away from what could be more optimal locally. And then ultimately people making their traffic even worse by building obstacles along the road. So street bumps slows traffic, stop signs slow traffic. And that's a reality of everyday city planning today to resist this influx of people that are coming to neighborhoods they would never have come to had they not had that information before. And so there's lots of different creative things done here. And I think the main interesting point is that obviously this might really lead to much bigger legal issues. And we already start to see the first lawsuits. Ironically, they happened in Israel where Waze was born. So it's kind of interesting return to the source. But we might really see some class actions in the US in not so long. And so the real question that is asked here is, is the information you're providing to people improving things? And obviously, for anybody who has studied game theory, we all know it to not be the case, except it's really hard to find good models to do this, and this is part of the work we're doing now. So just to give you a sense of the extent of the problem today, this is where we have seen these news pop up in just the popular media. Over 3 minutes? Okay. Got a bit late. 5? Can I negotiate to 5? Okay. So this is an example of where we see these things happening in the news. You can imagine it happens in many other places if it's just bad enough locally to make it into the news. And so let me give you an illustration of what's happening here. This is a simulation. It's not a theoretical result. But what we are showing here is a situation in which nobody had the information. So you could see this as what would have happened 10 years ago. And in a situation in which 20% of the people are using the information. So this is 1 minute clip. What you will see here is first traffic accidents. That's the daily routine of this corridor, leading to immediate backlog on the freeway. That's also fairly common. If people have the information, then people reroute. Okay, pretty intuitive as well, as opposed to just staying on the freeway not knowing. And then what happens when people reroute is that there is a chain of events that essentially lead to the system to operate at much worse condition than it would be had people had not the information. And so typically, first, what happens is that the residual congestion clogs the freeway even after the incident is cleared. That creates even more traffic in the freeway. So that's interesting how now the value of information becomes really negative. And then what you will see in the next few minutes of few seconds of the movie is that after that, all this traffic, which is rerouted on the arterial streets, makes it even worse there, just because these streets are not designed to support that extra traffic, and the signal timing plans at the intersections are also not timed properly to react to this. And then the movie goes on, and you can see this chain of events. And so since I don't have a lot of time to finish, maybe I can just finish by showing one model which is a static model, which is a model we've used to characterize this. And in this model, which is a Nash-Stackelberg model, the type of curves that we're producing can be summarized like this. So what happens is, very simple toy example, in which we have demand from here to here, and with the percentage of people using the app by solving a simple Nash-Stackelberg problem in which you assume that you have leaders who have the information and followers who don't have the information and route themselves selfishly, what you can compute is the travel time on the freeway, which is what people would have done had they if they had not had the information at 0%. And then as more and more people get the information, the flows start to deviate onto the first route here, and then you can see the travel time increasing, and then after a while, then it gets so bad that they start to deviate on the second route here, and that's the second increase until the travel time equalizes. And obviously, that's the definition, or that's a manifestation of a Nash equilibrium, at which point there is no incentive for anybody to deviate from their situation, because whatever you do, if you deviated, you would be worse off. And so the way these problems are solved is typically, we have shown that for parallel networks, if you pose the Nash-Stackelberg problem with a latency function that is monotonically increasing, same framework as Timur Gordon did with Eva Tardos almost 10 years ago for the internet, then the problems are convex, and then we can solve them in some specific cases in polynomial time in a number of links. So I'm going to stop here because otherwise we'll be out of time. But maybe the takeaway message here is that when you look at the statements made by elected officials specific to the optimality, they're wrong, because obviously we all know that there is a price of anarchy, and that except in some very specific cases it's non-zero. So the solution that is provided by providing people with selfish routing is not going to lead to global optimum solutions. But the open question that we're working on, and certainly that is not solved in a dynamic case, is how to arbitrate. Because it turns out that, in fact, Nash allocations might be good for very specific subnetworks of the whole transportation system. For example, it does do good to the freeway. Obviously, there's an externality that is suffered by the cities. And so the real question here is, given that this is going to happen because we're not going to be able to regulate this industry, how should the arbitration happen so that maybe the cities get compensated for the loss incurred? And that's an open problem for which there is no good answer to this day. So since we're out of time, I'm going to stop here. Thank you.
We have time for a question while Sid is setting up. Yep.
Maybe on the plot that you showed at the end, with 5% penetrations, things look pretty good. Like there was significant improvement on the I-2010, but like Pasadena wasn't really hurt.
Exactly.
So do you have ideas on how to induce basically that behavior as opposed to?
So there is a program called the Connected Cities program that Waze has been running, in which they are exchanging data with cities. It's not so much of a traffic management program as much as a data exchange program. But I think with some amount of coordination in which companies providing that routing would be able to not give that information to more than X amount of people, at least they would get to that point. The question is, for those who don't get an optimal route, how do you compensate them for that loss? And in fact, Balaji has been working on that second part of the problem quite a lot, because for traffic, it's a nut which is very hard to crack.
Yeah, there's also the other problem, which is, it's not just Waze, right? It's Google Maps is doing its own recommendation different from Waze.
Yep.
And there's iPhone with Apple Maps, and these don't all consult each other.
So it's not only within one app, but also coordination within apps, which you can imagine is traditionally even harder, because I mean, how are you going to get Apple and Google to coordinate on things where they're actually competing?
Yeah. Well, thanks, Alex. think I'm, as a co-organizer with David,